Hey everyone, I'm Mr. A, and today I want to talk with you about an angle of elevation versus an angle of depression. This is a very popular topic that comes up when you're studying trigonometry or geometry. A lot of times those appear together. And when we talk about an angle of elevation versus an angle of depression, an angle of elevation is when we are looking up at something. So think angle of elevation is looking up, angle of depression is looking down. Now, up and down are relative terms. There's no such thing as up in an absolute sense, right? If you imagine right now, if you all pointed up, you'd be pointing up from the ground, but if someone on the opposite side of the world was pointing up, they'd be pointing in exactly the opposite direction as you. So up and down are always relative to something. In this picture here, we've got us, let's say that's us, on top of this lighthouse, and then we have our friend down here on the ground waving to us. If we were to look at our friend, we would, of course, I think all agree that we'd be looking down at our friend. But looking down from where? An angle of depression is when we look down from horizontal. So it's not just looking down, it's looking down from horizontal that is the key here. So the angle of depression would be the angle from the horizontal line down to our friend. That's this angle right here. I'll call it theta. So that theta is the angle of depression. Now an angle of elevation is looking up. Again, from what? Still from horizontal. You're looking up relative to horizontal, which means that this would be an angle of elevation, looking up at us on the lighthouse. Our friend down here would be looking at an angle of elevation to get to us. I've already used theta, so I might need a new variable here, except I'm going to use theta again because I'm going to claim those angles have to be the same. Think about why for a second. If this line is horizontal, and this line is also horizontal, those have to be parallel lines then, don't they? Which means that these two angles, the angle of elevation here and the angle of depression here, those are alternate interior angles. Theta in blue is the angle of elevation. And the most important thing to remember is this relative position. Again, it's looking down from horizontal for an angle of depression. It's looking up from horizontal for an angle of elevation. As long as you remember those horizontal lines, then there's not a whole lot to trip you up. So let's take a look at a few examples of how this would be used. Of course, you're going to need to know sines, cosines, and tangents, and the inverse trigonometric functions. If you need a reminder on any of those, I'll put a link in the description to videos on both the regular trig functions and the inverse trig functions for you. Let's say we're in the woods and we spot a bald eagle up in a tree. We measure the angle of elevation to the eagle to be 67 degrees. I'm going to underline that because that's an important piece of information, right? 67 degrees is this angle of elevation. We walk directly to the tree and determined that we were standing 150 feet from the tree when we saw the bald eagle. So we were 150 feet from the tree when we saw that eagle. The question is, how high up was the bald eagle? So clearly we need a picture here. Now there's two kinds of people in the world. There's the kind of people that will draw this like this. So there's the tree. We were over here on the ground when we looked up and saw the eagle. And there's absolutely nothing wrong with that picture. We assume that trees grow perpendicular to the ground, so we can call that a right angle. The angle of elevation was 67 degrees, so if this is us over here, right, then they're telling us that this is a 67 degree angle that we're looking up at the eagle. We were standing 150 feet from the tree, and how high up in the tree was the bald eagle? Let's call that X. That mathematically captures everything we need. In fact, we don't need that person there. I got a little carried away. If you want to draw a little tree, that's totally fine too. Just don't take like forever on your tree, right? Give it a little bit of detail if you want. So this is a basic trigonometric question. You think about the angle, 67, across from it, that is the opposite side of the triangle. This side is the adjacent, because the side across from the 90 would have been the hypotenuse. Since we don't know that one, we'll ignore it, and we'll just use the opposite and adjacent. With those two, we can set up a tangent equation. We can say that the tangent of 67 is the opposite side, x over the adjacent side, 150. Put that over 1 and cross multiply. X is equal to 150 times the tangent of 67. So I'll grab my calculator, and I have approximately 353.37. Okay, let's just round that to 353. There are no rounding instructions, so of course follow whatever instructions are in the problem. And that's how tall the eagle is in the tree. Notice that in order to answer this question, we had to know that the angle of elevation was the angle that we're looking up from horizontal at the eagle. Let's take a look at an angle of depression. So for this one, let's say we're on top of a building and we look down to see our friend on the street. If the angle of depression is 57 degrees and the building is 200 feet tall, how far away from the bottom of the building is your friend? Mathematically, all we really need to capture what's going on here is a triangle. But if you want to, draw a little building, we got some windows there and a door. So, of course, when we look down at our friend, we're looking at an angle of depression. But remember, what does an angle of depression mean? That means we're looking down from horizontal. So here's the classic mistake. Pay careful attention. I see a lot of students put that 57 degrees here. That is incorrect. That is not the angle of depression because you're not looking that angle down from horizontal. So the thing you want to be very careful about with an angle of depression problem is always draw in the horizontal line. Because until you do, you can't really see your angle of depression. As soon as you put that horizontal line in, then you can see that this is the angle that you are in fact looking down from horizontal at your friend. And of course, that angle is outside of the triangle now, right? So the triangle, here's the right angle. The building is 200 feet tall. So this side of the triangle is 200. But there's no angle here, right? This 57 is outside the triangle. Well, that's where those alternate interior angles come in that we talked about before. If that angle is 57, so is this because this is horizontal. And of course, we assume the ground is horizontal. And here we have this setup. So I could extract all that information into just a pure triangle. It would look like this. And we're trying to find how far away from the bottom of the building is our friend. That's that distance there. We'll simply start off by finding the angle in the triangle. Across from it is the opposite side. This one is the adjacent side. Across from the right angle would be the hypotenuse. And again, we have the opposite and adjacent. So this is another tangent problem. We can say that the tangent of 57 is the opposite 200 over the adjacent x. That will give us x times the tangent of 57 equals 200. And here we still need to divide both sides by tangent of 57. So x is actually 200 divided by the tangent of 57. And if you plug that in your calculator, you'll get a 129.88. So I'm just going to go ahead and call that about 130 feet. Again, this problem is one that trips a lot of students up because you don't take the time to draw that horizontal line. And if you don't put that horizontal line in, it is very easy to put the 57 degrees here. But that will be a completely different triangle and it will give you a wrong answer. So be careful about that. When you're doing an angle of depression, always draw that horizontal line. One more example because there's an extra little wrinkle in this problem. If we're flying a kite in the park and your friend notices that the angle of elevation from your hand to the kite is 63 degrees. That happens all the time, right? If the kite is 100 feet off the ground and your hand is 5 feet off the ground, how much string is between you and the kite? Let's try to build a picture here first. If I've got a kite flying up in the air, and here's my little kite. Every kite needs a tail. If you've ever flown a kite, you'll know that that string is not straight. It actually curves like this. But for a mathematical problem like this, they typically assume that the string is straight. Now here's the thing. If our hand is 5 feet above the ground, well then the triangle is actually 5 feet off the ground too, isn't it? Like here's the triangle that this problem is all about. So if I just pull the triangle out, I only need 95 here because the other 5 feet is the part that's underneath the triangle, this section here, right? This little rectangle that's 5 by whatever. So I have to take that off the height of the kite. The angle of elevation they told us was 63 degrees. And of course, we're looking for how much string is out. That would be that side of the triangle. So to solve this, we would start at our angle and look across from the triangle. There's our opposite side. This, of course, is our hypotenuse because that's the right angle right there. So with an opposite and a hypotenuse, we can set up a sine equation. We can say that the sine of 63 is the opposite 95 over the hypotenuse x. Cross multiplying, we get x times the sine of 63 equals 95. And then to solve for x, we need to divide both sides by the sine of 63, which gives us x about 106.6. So I'm just going to call that about 107 feet of string. So do be careful about a little detail like that. If they give you the height of the person or the height of the string for a kite or something like that, just realize that your triangle's off the ground and you have to account for that in your problem. So the last three, all we're looking at finding a missing side, but we can also use angles of elevation or depression to find missing angles. So let's say we're standing on level ground, 800 feet from the base of a store. Now the store has a flag on the top of the building, and if it's 50 feet high, the building that is, what angle of elevation would you need to look in order to see the flag? So the building is 50 feet tall, that's this side here, right? The height of the building is 50. And we are down here on the ground, and we're going to look up at this flag, and we're going to see it at some angle of elevation. We do know that we are 800 feet from the base of the store, right? So this distance here is 800 feet. Again, we can abstract this into just a triangle. Also, since no information was given about the height of the person or our height in this problem, we just assume that that angle is the angle that we are from the ground. And solving in this triangle, we can say theta is here, which means across from it is the opposite side of the triangle. This, of course, would be the hypotenuse across from the 90. making the 800 the adjacent side. So I have an opposite and an adjacent, which means this is going to be a tangent problem. The tangent of theta is the opposite over the adjacent side. Now that's true, but it's not helpful because what I really want is to get to that angle theta there. So I need to know what angle has a tangent of 50 over 800. So in our calculator, we're going to say, well, theta is the inverse tangent of 50 over 800. Get to that in your calculator as you hit the second key and then the tangent button, and our calculator will tell us that that angle theta is approximately 3.576. So let's just go with about 3.6 degrees. Take a look at one last problem, this time with an angle of depression. Let's say you're in a hot air balloon flying over Long Island when you spot your house. If the balloon is 1,000 feet in the air and the distance from your house, from you to your house, is 10,000 feet, what is the angle of depression you're looking at when you see your house? And of course, we're here in the basket. Here's distance in the air, and then somewhere down here on the ground, we look down and we see our house. What do we know here? The balloon is 1,000 feet in the air, so this side of the triangle would be 1,000. The distance from you to your house is 10,000 feet. Now think carefully, where does that distance need to go? Is this the distance from you to your house? No, it's this side of the triangle, right? There's you, there's your house. So this is the 10,000. Of course, this is a right angle because that's how we measure height. And what we're trying to find is, what is the angle of depression that you are looking at when you see your house? So remember, what an angle of depression is looking down from horizontal, which means the actual angle this question is looking for is this angle here. Now that angle is not inside of this triangle, but that's okay because it's down from horizontal. That is the same as this angle because these are alternate interior angles. So we're just going to solve for that angle right there. Of course, we can abstract this to simply a triangle. Start at the angle, look across from it. That's our opposite side. This is the hypotenuse, so we don't need the other side, but that would be the adjacent side. With an opposite and a hypotenuse, this one's going to be a sine problem again. So we can say that the sine of theta is the opposite 1,000 over the adjacent 10,000. So this is a true statement, but it is not terribly helpful because what I need to know is what's the angle that has a sine that is 1,000 over 10,000. That's an easy question to answer as long as we have a calculator handy. Theta equals inverse sine, so sine with that -1 of 1,000 over 10,000. To get that, again, you hit the second button and then the sine button, and you'll get that that angle is approximately 5.739, and that's pretty much all there is to angles of elevation and angles of depression. It's a very simple topic, but in my experience, it's one that's very easy to trip students up, particularly when you have the angle of depression. If you just remember to draw that horizontal line and that the angle is from horizontal down, then you'll be okay. It's putting the angle here that gets you. Same thing, if you put the horizontal line first, then you can see your angle of depression in that spot. If you put it here, which is a very common mistake, that's the thing that gets you. So just remember, angles of elevation are looking up from horizontal, angles of depression are looking down from horizontal. If you enjoyed this video, please give it a like, subscribe to my channel, feel free to leave a comment below, and as always, have a great day.